Okay, so in this video I'm going to do a proof by induction of a series. So I've got a series here on the left hand side, and we want to see if that's equal to 2 to the power of n minus 1, where n is just a natural number. So this is a series on the left hand side here, because let's say if r is equal to 1 here, we would get 2 to the power of 1 minus 1, which is 0. So that's really just 1. And we need to add these up. The sigma here just means add them up, so we're adding up. The next one is r is equal to 2. So if you let r equal to 2 here, you get 2 to the power of 2 minus 1, which is just 2. Look at the next one then. That's just going to be r is equal to 3. 3 minus 1 is 2. 2 to the power of 2 is 4. And so on. This keeps going on. If r is equal to 4, that would be 4 minus 1 here, which is 3. 2 to the power of 3 is 8. And so on. That just keeps going on forever. And eventually you get to 2 to the power of r minus 1. Okay, so that's our series here on the left hand side. And we just want to see, is that equal to 2 to the power of n minus 1? Okay, so the first thing you do when you're proving by induction is to take the lowest natural number here. In this case it's 1. And just let n equal to 1. So if n is equal to 1, what happens? Well, on the left hand side we see we'll end up with 2 to the power of 1 minus 1, which is 2 to the power of 0, which is 1. We've already done that here. But on the left hand side we get 1 when n is 1. On the right hand side, when n is 1, we get 2 to the power of 1 minus 1. So n here in this case is just 1. 2 to the power of 1 is 2, so 2 minus 1 is 1. So we see here that the left hand side will be equal to the right hand side. So we can see here that the proposition is true. We'll call it P for proposition, is true when n is 1. So that's the first thing you need to do in any of these proofs by induction. Now, so the next thing we've got to do then is look at assuming that this is true for p is equal to some value k. So we're going to assume that the proposition is true. Assume that it's true for some proposition, or for some number rather, k. So we're going to assume true for pk. So what happens if we put k in here instead of n, in other words? So we end up on the left hand side with the sum of or actually, you know what we'll do? Instead of writing this out, this here is just this here. I've written it out here as a series, as you're familiar with. So this and this are exactly the same thing. So I'm just going to write it out like this: 1 plus 2 plus 4. So we'll just write that out. So we want to assume that I'll do it in a different color here. Let's say 1 plus 2 plus 4 plus, and so on, all the way up to here, this part here, 2 to the power of k. Now remember the n here is changed to k, or the r is changed to k, so it's k minus 1. So that's on the left hand side. We're assuming that on the left hand side we have this, on the right hand side we've got 2 to the power of k, and then minus 1 here. So we're assuming that this is true. Okay, so what do we actually need to prove then? We need to prove that the proposition is true for p k plus 1. That if the proposition is true for some number k, then it will always be true for the next number up, k plus 1. So we need to prove that. Again, I'll do that in blue here. So we need to prove that 1 plus 2 plus 4 plus, and so on, up as far as here, 2 to the power of k minus 1. But now we've got to add a k plus 1 in there, so we have another term here. So that's plus 2 to the power of k plus 1 minus 1. So instead of the k here, I've got to put in a k plus 1. And then this minus 1 is this minus 1 here. And then on the right hand side I do the same. I've got 2 to the power of, instead of the k, now I've got a k plus 1, and I've got that minus 1 there. So we want to prove that this here is true. If it's true for k, it will be true for this. That's what we want to prove. Now, the way you tackle these is that you look at this part of your series here. This part of the series here is the proposition, or the assumption rather, pk. So is this part here of our assumption. We're assuming this is true, so we're saying that this part is true. So this part here is equal to 2 to the power of k minus 1. So in other words, instead of this part of what we want to prove, we can just write in 2 to the power of k minus 1. So this is just 2 to the power of k minus 1. That's 2 to the power of k minus 1, up as far as here. But we've also got this bit here. So that's 2 to the power of k plus 1 minus 1. That's just simply 2 to the power of k. The ones here will cancel. So all of this here really is just this part here, this here. And we want to prove that that's equal to 2 to the power of k plus 1 minus 1. So can we show the left-hand side here is equal to the right-hand side? Let's see. Well, we have a 2 to the power of k here, and we have a 2 to the power of k here. So we have two of them. So that's just 2 times 2 to the power of k. This dot here is just multiply. And then we have this minus 1 here as well. On the right hand side, we want to see if it's equal to 2 to the power of k plus 1 minus 1. So what do we end up with here? Well, we have 2 to the power of 1 here times 2 to the power of k. That's 2 to the power of k plus 1 by our rules of indices. And we have our minus 1 here. And on the right hand side, we still have k plus 1 here minus 1. So we have shown that the left hand side and the right hand side are equal. So what have we actually done? We have shown that if we assume that the proposition is true for some number k, if it is true for k, then it will be true for the next number k plus 1. So if the proposition pk is true, then pk plus 1 will be true. Now, how does that help us? Well, we know that the proposition is true for 1, n is equal to 1. This is true. So we've just shown up here that if the proposition is true for some number k, it will be true for the next number. Now let's say that k is 1. If k was 1 here, then the proposition would be true for 2. K plus 1, in other words. 1 more than 1, which is 2. And if it's true for 2, then the proposition would be true for the next number, 3. If it's true for 3, the proposition will be true for 4, and so on and so on. And this is our proof by induction. So we've shown that the proposition is true for 1, n is equal to 1. This is true. If you would write it like this, if pk is true, then pk plus 1 is true. I think I've written that right, have I? I'll just rewrite it here. Is true. So if the proposition is true for k, it's true for pk plus 1. We know it's true for p1. Therefore, you can say, therefore, by induction, the proposition is true for all n is an element of n. And that's it for this series anyway.